5.2 Lesson 1, Linear Approximations and Differentials. Our objectives are 1, you will understand the concept of local linearity and how it can be used to approximate a function with a linear function, and 2, you will know the definitions of differentials and be able to find the differential of y dy. This is our first example. It is, in fact, example 1 from the textbook, and we have this problem. For f of x is equal to 15 minus x cubed, find the particular equation for L of x, the linear function whose graph is tangent to the graph of f at the point 2, 7. So just focusing on that sentence, we want to focus on one particular word. Graph is tangent to. The particular word that we want to focus on is tangent, tangent to. So we have a graph that is tangent to the graph of f at this point. So our first question is, what is the slope of that tangent line? What is the slope of the tangent line to the graph of f at x is equal to 2? How can we find that slope? What do we need to do? To find the slope of the tangent line to the graph of f at x is equal to 2, we have to find the derivative of the function f and evaluate the derivative at x is equal to 2. So we have f of x is equal to 15 minus x cubed. So f prime of x is equal to negative 3x squared. And now we will evaluate the derivative at x is equal to 2, and we'll have negative 3 times 2 squared. So 2 squared is 4. Negative 3 times 4 is negative 12. So that is the slope of the tangent line to the graph of f at x is equal to 2. So what is it that we want to do? We want to find the particular equation for the tangent line to the graph of f at this point of tangency. To answer this question, we'll remember something called the point-slope form of the equation of a line. This is something that we reviewed at the beginning of the course all the way back in August. Point-slope form. And right now we know the slope of this tangent line. It is negative 12, so I can substitute negative 12 for m. And we know the coordinates of a point that will be on the tangent line, and that point is the point 2, 7, called the point of tangency. So that's going to be x sub 1 will be 2, and 7 will be y sub 1. So we're going to write y minus 7 is equal to m, which is negative 12, times x minus 2. So we can now add 7 to both sides of the equation, and that would give us y is equal to negative 12 times x minus 2 plus 7. And what is this? This is the equation of the tangent line to the graph of f at x is equal to 2. For f of x is equal to 15 minus x cubed, find the particular equation for L of x, the linear function whose graph is tangent to the graph of f at the fixed point 2, 7. So we've done that. It's right here. Show graphically that f is locally linear at x is equal to 2. What is this concept of local linearity? Show graphically that the function f is locally linear at x is equal to 2. So in red here, I have the graph of f, and in blue here, I have the graph of L, the linear approximation to the graph of f at x is equal to 2. And this is, of course, the point 2, 7. What does it mean that the graph of f is locally linear at x is equal to 2. To help you see exactly what we mean by that, we're going to zoom in to about this part of the graph. And when we look at the zoomed in graph on the right, you'll see that here we have x is equal to 2, here we have y is equal to 7, and the red graph once again is the graph of the function f, and the blue graph is the graph of the linear approximation for the function f at x is equal to 2. You can see that the graph of f is nearly indistinguishable from its tangent line for x values that are close to 2. That is what is meant by locally linear at x is equal to 2, meaning that the graph of f can be approximated pretty well with a line for x values that are close to the x value of the point of tangency. That is the concept of local linearity. Show numerically that L of x is a close approximation to f of x for values of x close to 2 by calculating the error in the approximation L of x is approximately equal to f of x. So we saw graphically that L of x is a good approximation for the function f for x values that are close to 2, as you can see here. The two graphs are nearly indistinguishable. So in the last sentence, we just want to verify this numerically, that L of x is a close approximation to f of x for x values close to 2 by calculating the error in the approximation L of x is approximately equal to f of x. So you can see that at x is equal to 2, f of x, the function f of x, when evaluated at 2, will give you an output of 7, and the function L of x, when evaluated at 2, will also give you the same output of 7. So at the point of tangency, the two functions have the same output. There is no difference between the two functions, so the error in approximating f with L of x at the point of tangency is 0, because the output values from the two functions f and L are identical. But as we go further away from 2, the error increases. And you can see that visually by looking at the graphs of the two functions. When x values are close to 2, the two graphs are pretty much indistinguishable visually. But as you get further away from 2, like for example here at x is equal to 2.2, you can see that there is a difference between the y values from the two functions. There's a difference between the two graphs. So for x values that are close to 2, there is not going to be much of a difference between the outputs of the two functions. However, for x values that are further away from 2, there's going to be some difference. And that's basically what this is asking us to do. Show numerically that L of x is a close approximation to f of x for values of x close to 2 by calculating the error in the approximation L of x is approximately equal to f of x. So we just find the actual value of the function given by f of x and subtract from that the approximate value for the function given by L of x, the linear approximation for f at x is equal to 2. So in this table, in this column here, we have output values from the function f at various input values for x. In the next column, we have output values for the function L, the local linear approximation for f at x is equal to 2, at these values of x. And in the last column, we want to see what the difference is between the output values from the two functions. And we see that the further we go from 2, the greater the difference. So the example that we looked at helped us with Objective 1, understanding the concept of local linearity and how it can be used to approximate a function with a linear function. we will take what we did in example 1 and just have a generic diagram going over the same concepts. So just like we saw in example 1, we have some function f, and in this general diagram, the graph of f is represented by this green curve. And it is going to be approximated by a tangent line, which I will now shade in blue, at the fixed point that is marked at x is equal to c. So now we would like to take a look at objective 2. You will know the definitions of differentials and be able to find the differential of y dy. What do we mean by differential? You can see here that it is marked in this general diagram as a difference in x values between the x value of the fixed point and some other x value that are close to some other x value that is close to it. So dx is talking about a difference in x values for 2 points on the linear approximating line, on the line that's giving us the linear approximation. So that's dx, the difference between the x coordinates of 2 points on the tangent line, where one point is the point of tangency and we have a second point. What is dy? dy is the difference between the y coordinates of 2 points on the tangent line, where one point is the fixed point, the point of tangency, and the other point is a second point on the tangent line. So dy is the difference in the y coordinates of 2 points on the tangent line, where one point is the fixed point and we have a second point. Dx is the difference in the x coordinates of 2 points on the tangent line, where one point is the fixed point and we have a second point on the tangent line. These are called differentials. So you will know the definitions of differentials and be able to find the differential of y dy. So how do we find the differential of y dy? And vocabulary is differential. To understand how to find dy, take a look at this right triangle. And of course, we have these two vertices of the right triangle, which are points on the line that is the tangent line to the graph of f at the fixed point. So I can actually find the slope of the tangent line by doing rise over run. And you can see as we go from the fixed point to our second point that the rise is given by dy and the run is given by dx. So we have rise over run. The rise is given by dy and the run is given by dx. And what does rise over run tell us? It tells us slope. And we know how to find slope for the function f. We have to find the derivative of the function f, because the derivative of the function f will give us the slope of tangent lines to the graph of f. So we need to find the derivative of the function f, because that will give us the slope. So how do we find dy in terms of the slope and dx? You just multiply both sides of this equation by dx and you get dy. This is the differential of y. It is f prime of x times dx. So you will know the definitions of differentials and be able to find the differential of y dy. Simply, to find the differential of y dy, you need to find f prime of x and multiply by dx. And you can see that stated here, definition and properties, differentials, algebraically, the differentials dx and dy are defined as dx is equal to delta x, and we'll see what that means now in a minute, but we just found dy is equal to f prime of x dx. I explained why that makes sense. Verbally, multiply the derivative by the differential of the inside function. Basically, you can ignore the part about the verbally, but we explained why this makes sense. So now let's look at the first part here. When you look at the second diagram, it's the same as our first diagram. So it's the same diagram, but we just want to emphasize what additional information we have. So the additional information that we have is as follows. This is our fixed point. And in the first diagram, we looked at a second point that was on the tangent line. And in the second diagram, in addition to the second point that's on our tangent line, we look at a second point that's on the graph of f. And these 2 points that we're looking at for the second point, they have the same x value. So when we talk about dx, it is the difference between the x values of 2 points on the tangent line. And when we talk about delta x, it is the difference in x values of 2 points on the graph of f. But dx is equal to delta x because we're looking at second points on the graph of f and on the tangent line at the same x value. So that's why this makes sense. And in example 1, we looked at the concept of error. And as we go from the fixed point to our second point, there is a change in the y-coordinates of the 2 points on the graph of f. And that change in the y-coordinates is delta y. As you go from the fixed point to the second point on the tangent line, there is a change in the y-coordinates of the 2 points on the tangent line, and that change in y-coordinates is dy. And of course, there's going to be a difference between delta y and dy, and that difference is called the error, as we saw in example 1. And that's basically the gap that you see there, because we know that although the tangent line is a good approximation for the function, the further you go away from the point of tangency, the less accurate the approximation becomes. Now we look at our second objective. You want to find the differential of y dy. And how do we do that? We use this definition that we just learned about. It's really easy. Find an equation for the differential dy. If you'd like to, you can rewrite what's given as f of x is equal to 7x cubed. And of course, you can find f prime of x very easily. Using the power rule, it's going to be 21x squared. So using this definition, the differential of y is simply f prime of x multiplied by the differential of x. The differential of y is 21x squared dx. And that's all you've got to do for number 9. Let's take a look at number 10 and number 11. So for number 10, we have y is equal to negative 4x to the 11th. You can write that as f of x is equal to negative 4x to the 11th. You can easily find f prime of x by using the power rule. So you'd have negative 44 x to the 10th. And if you want to find dy, here's all you've got to do. You're going to do f prime of x dx by definition. So all you have to write is dy is equal to negative 44 x to the 10th dx. And let's take a look at number 11 as our last example for today. Same instructions, find an equation for the differential dy. So for number 11, we have y is equal to x to the fourth plus 1 to the seventh power. You may write that as f of x is equal to x to the fourth plus 1 to the seventh power. So now we have f prime of x. You can find f prime of x by using the chain rule. Our inside function is x to the fourth plus 1, and our outside function is raising to the seventh. So f prime of x would be 7 times x to the fourth plus 1 to the sixth, multiplied by the derivative of the inside function with respect to x, and the derivative of the inside function with respect to x is going to be 4x cubed. So we're going to have multiplied by 4x cubed plus 0. The derivative of 1 is 0, so I have plus 0. So f prime of x, if I were to simplify it, would be 28x cubed x to the fourth plus 1 to the sixth power. So what is dy for number 11? dy is, by definition, f prime of x times dx. So all we have for number 11 is dy is equal to 28x cubed times x to the fourth plus 1 to the sixth power times dx. And that's how you do these problems. Find an equation for the differential dy. So today we looked at an example to help us understand the concept of local linearity and how it can be used to approximate a function with a linear function. And we also looked at objective 2. We looked at understanding the definition of the differential of y dy. And to help us generalize from objective 1 and building a bridge to objective 2, we looked at these two general diagrams.